We are Edward, Kerrie, and Zhichao, and we are presenting our final project, which is titled Collaborative Pick-and-Place Between Tandem Robotic Arms with Deep Q Learning. We are interested in applying deep learning to robotics. One problem in robotics that is really applicable to manufacturing tasks is pick-and-place tasks, especially where multiple agents need to collaborate with each other. We have created a simulated task environment where we have two 4 degrees of freedom robotic arms in a 3D space. Each arm is controlled by a separate agent. There are 2 tasks that we are trying to accomplish. The first task, which we call the pick and place task, or the A to B task, involves moving 5 tokens from the start location to the checkpoint location in the center of the workspace, where the other arm can reach. This is a simple and non-interactive task. The tandem passing task is for both arms to first accomplish the pick and place task, and then also move the tokens that it has received from the other arm to a desired bin location within its reach. This requires coordination with the other arm. There are a number of deep reinforcement learning algorithms that have been useful for robotic control tasks. One existing approach is called deep deterministic policy gradients, which have been used for collaborative control of a 2-arm robot. And another approach is called DQ networks, which have been used to play Atari games with great success. We chose to apply DQN to our task because it is useful for the discrete action space that we have specified. DQN refers to using a deep learned network to approximate a value function used in Q learning. We train a network that takes in an observation from the environment and outputs Q values for each possible action. We can then choose the action that maximizes the Q value at each time step of the simulation to accomplish the overall task. We've implemented our task environment and built our model using existing libraries such as Stable Baselines 3, PettingZoo, and OpenAI Gym. We've trained both the tandem passing task and the pick and place task separately. We find that we can reliably solve the pick and place task, and we can partially solve the tandem passing task.
When trained on the single step task, the robots move tokens to the center of the court without interaction. They receive a large discrete reward for picking up or placing a token, and a smaller continuous reward based on their distance to the target pickup or bin location. The robots complete this simple pick and place task with 100% success, following their respective Q policy with probability 0.5 and taking a random action with probability 0.5. In the tandem multi-step task, the robots are rewarded for sequentially bringing their partner's token to the center of the court and receiving their own token to deposit it in their bin. With multiple competing objectives, the agents do not always transition correctly. The robots successfully score about half of their tokens using a random action probability of 0.5. The effects of these random actions on task performance were closely investigated. When following a completely random policy, or when deterministically following their learned Q policy, the agents score no tokens. Optimal performance is achieved when the agent follows a stochastic policy by taking a random action with probability 0.75. This work shows that multiple agents can learn to work together with deep Q learning. The performance decreases with increasing task complexity. Stochastic policies offer a potential improvement in multi-step collaborative settings.